In last class, we had discussed about unit cell and types of unit cells. What is unit cell? It is the part of the crystal lattice which when repeated gives you the entire crystal. And what are the different types of unit cells? Unit cells are two types, primitive unit cell and centered. Primitive unit cell is also known as what? Simple cubic unit cell. And centered unit cells are which all? Body-centered cubic unit cell, face-centered cubic unit cell and end-centered unit cell. So today in this class we will see how to calculate the number of particles per unit cell. So in last class also we had discussed the contribution of a particular particle towards the unit cell. So a particle at the corner of the unit cell is shared by 8 unit cells. So the contribution to that particular unit cell is how much? 1 by 8. So corner's contribution is 1 by 8. Then a particle at the center of the body of the unit cell belongs to that particular unit cell. So the contribution is how much? 1. So center of body contribution is 1. Then a particle at the face center is shared by 2 unit cells. So the contribution is 1 by 2. So center of face 1 by 2. Then a particle at the edge center is shared by 4 unit cells. So the contribution is 1 by 4. So center of edge, the contribution is 1 by 4. So these things you have to remember. A particle at the corner, contribution is 1 by 8. Center of the body 1, center of the face 1 by 2 and center of the edge it is 1 by 4. So based on this, we will see how to calculate the number of particles per unit cell. So first we'll see is about simple cubic unit cell. Number of particles per unit cell in case of simple cubic unit cell. So we'll be using the abbreviation SC. SC means simple cubic unit cell. I'll just draw it. So what is a simple cubic unit cell? A unit cell which has got constituent particles only at the corners. So how many corners are there? 8 corners, and we know the contribution at the corner is how much? 1 by 8. So what will you write? Number of particles. I am not writing it as atom or molecule. Just I am specifying number of particles. The particles can be what? Atoms, molecules or ions. Number of particles per unit cell in case of simple cubic unit cell. So you have got it only where? At the corners. So 8 corners. And what is the contribution at the corner? 1 by 8. So how much it will come? 1. So what is the number of particles per unit cell in case of simple cubic? 1. So in case of a simple cubic unit cell, the number of particles or atoms or molecules or ions is equal to how much? 1. So what is a simple cubic unit cell? A unit cell which has got constituent particles only at the corner and its contribution towards that particular unit cell is how much? 1. So number of particles per unit cell in case of simple cubic unit cell is equal to how much? 1. Is it clear? Now next we'll go for is number of particles per unit cell in case of body-centered cubic unit cell. Body-centered cubic unit cell, and it is known as BCC. The short form we'll be using is BCC. Now see, what is a body-centered cubic unit cell? A unit cell which has got constituent particles at the corner. Apart from the corner, it has got a particle at the center of the body. So a unit cell which has got a particle at the center of the body apart from the corner position is known as what? Body-centered cubic unit cell. So we'll calculate number of particles per unit cell in case of body-centered unit cell. So it will be how much? 8 corners into 1 by 8 plus at the center of the body. One center of the body. And what is the contribution? It's 1. So how much it will come? 1 plus 1, it's equal to 2. So the number of particles per unit cell in case of BCC unit cell is how much? 2. So understood what is a body-centered cubic unit cell? A unit cell which has got a particle at the center of the body apart from the corner position is known as body-centered cubic unit cell, and number of particles per unit cell is how much? 2. So is it clear? So the next one is face-centered cubic unit cell. It's also known as FCC. So now what is a face-centered cubic unit cell? A unit cell which has got constituent particles at the center of each face apart from the corner position. So center of the face means each face will have. Now here I am going to draw 2. Why? 1 in front and 1 behind. So total how many faces are there? 6. 1, 2, 3, 4, 5 and just 1 behind, that is the 6th face. So a face-centered cubic unit cell is a unit cell which has got constituent particles at the center of the face apart from the corner position is known as a face-centered cubic unit cell. So the number of particles per unit cell in case of a FCC unit cell will be how much, you see? Corner position 8 corners into 1 by 8 plus how many faces are there? 6 faces, and its contribution is what? 1 by 2. So total it will come how much? 1 plus 3, that is equal to 4. So number of particles per unit cell in case of FCC unit cell is how much? 4. So is it clear? So FCC unit cell is what? A unit cell which has got constituent particles at the center of the face apart from the corner position is known as a face-centered cubic unit cell, and the number of particles per unit cell in case of FCC is how much? 8 corners into 1 by 8 plus 6 faces into 1 by 2. So total it will come how much? 4. So in case of simple cubic unit cell, number of particles per unit cell is 1. In case of BCC, the number of particles per unit cell is 2. And in case of FCC, the number of particles per unit cell is how much? 4. So is it clear? Now next one is end-centered unit cell. What is an end-centered unit cell? End-centered unit cell. So in case of an end-centered unit cell, the particles will be present at the corners and any 2 alternate faces. If it is present here, then it will be present here. If it is present here, here. Either here and then behind. So any 2 opposite faces will be occupied. Such a unit cell is known as what? End-centered unit cell. A unit cell having constituent particles in any 2 of the opposite faces apart from the corner position is known as a end-centered unit cell. So the number of particles per unit cell is equal to 8 corners into 1 by 8 plus how many faces are occupied? 2. So 2 into 2 faces occupied, and its contribution is how much? 1 by 2. So what will be the number of particles per unit cell? It will be 2. So end-centered unit cell has got constituent particles in any 2 opposite faces apart from the corner position is known as end-centered unit cell. So is it clear? So this part is important. Why? Because when you do numericals, the equation itself, they will be just saying it will be having a simple cubic structure or a BCC structure or a FCC structure or end-centered structure. So you should be able to write the number of particles per unit cell. So for simple cubic unit cell, the number of particles is equal to 1. For BCC, the number of particles is 2 per unit cell. And for FCC, the number of particles is 4 per unit cell. And case of N-centered unit cell, the number of particles is how much? 2. So now we'll do a simple few numericals related to number of particles. See, just write this question along with me. A crystal is made up of atoms A and B. The A atoms occupy the corner position of the cube, and the B atoms occupy the edge center. What is the formula of the solid? A crystal is made up of atoms A and B. The atoms A occupying the corner position of the cube and the B atoms occupy the edge center. What is the formula of the solid? Now, how will you do this question? See here, it is made up of two atoms A and B. So, you have to calculate the number of A atoms and number of B atoms. Now, how will you calculate? See here, number of A atoms. Now, the A atom is occupying which position? It's occupying the corner position. So, how many corners are there? 8 corners. And what is the contribution of the corner? It's 1 by 8. So, what is the number of atoms? 1. Then, next you see, the B atoms occupy the edge center. So, you have to calculate the number of B atoms. So, it's occupying the edge center. How many edges are there? 12 edges. So, 12 edges into 1 by 4. So, it is equal to how much? 3. So, what will be the formula? A1, B3. Or you can write it as what? AB3. So, is it clear? A crystal is made up of atoms A and B. The A atoms occupy the corner position of the cube and the B atoms occupy the edge center. What is the formula of the solid? So, you have to see the number of A atoms and number of B atoms. So, number of A atoms is equal to 1 and number of B atoms is equal to what? 3. So, the formula is what? AB3. So, let us discuss one more question. Ionic crystal is made up of ions X and Y. X occupies half of the corner and Y occupies the center of the body. Of the crystal. Find the formula of the crystal. So, an ionic crystal is made up of ions X and Y. X occupies half of the corner and Y occupies the center of the body of the crystal. Find the formula of the crystal. So, first you are finding out number of X ions. It's occupying what? Half of the corner. So, how many corners are only occupied? Total how many corners are there? 8. Only half is occupied. So, it will be what? 4. So, 4 into 1 by 8. So, how much it will come? 1 by 2. Then, Y occupies the center of the body. So number of Y ions equal to what? Center of the body contribution is 1. So 1 into 1. So it is equal to what? 1. So the formula will be what? X 1 by 2, Y 1. Or you can write it as what? X, Y 2. So is it clear? So number of X ions are occupying what? Half of the corner. Half of the corner means total 8 corners are there. Only 4 are being occupied. So the contribution is 4 into 1 by 8, 1 by 2. And number of Y ions is equal to 1 into 1, which is equal to 1. So the formula will be X 1 by 2, Y 1 or X, Y 2. Is it clear? See, these are the 7 different types of crystal systems. And they are also known as Bravey's lattice. Okay. So you have got cubic, tetragonal, orthorhombic, hexagonal, trigonal, rhombohedral, monoclinic and triclinic. Last class itself I had explained, no? In case of a unit cell, there are 6 parameters. That is the 3 edges and 3 angles. So here you see the edges A, B, C and the angles alpha, beta and gamma. And what did I say? That is the edges, they can be, the 3 edges can be equal or they may not be equal. And the angles also, they may be equal or they may not be equal. Now see here, in case of a cubic crystal type, the 3 axial edges are same and the axial angles are also what? Same. And they can be either primitive, BCC or FCC. Then comes tetragonal. There A is equal to B but not equal to C. Alpha is equal to beta equal to gamma equal to 90 degree. And it can be either primitive or BCC. Primitive is also known as what? Simple cubic unit cell. Then comes orthorhombic, where A is equal to B, B not equal to C, alpha equal to beta is equal to gamma equal to 90 degree. And it is primitive, BCC, FCC or end-centered. Or it can be end-centered. So the example is barium sulfate, calcium sulfate. Then comes hexagonal. Here A is equal to B, B not equal to C, alpha equal to beta equal to 90 degree and gamma is equal to how much? 120 degree, and it's only which type? Primitive type, and it's graphite. Then comes trigonal or rhombohedral. Here A is equal to B is equal to C, alpha equal to beta equal to gamma not equal to 90 degree, and it's primitive type only, and example is calcium carbonate. Then comes monoclinic, where A not equal to B not equal to C. The angles alpha is equal to gamma equal to 90 degree and beta not equal to 90 degree. And it's either primitive or it can be end-centered. Example is monoclinic sulfur. Then comes triclinic, alpha, sorry, not alpha, A not equal to B not equal to C, alpha not equal to beta not equal to 90, gamma not equal to 90 degree. An example is primitive, it's primitive type, and the example is potassium dichromate. Okay, so these are the different types of unit cells. This you should be clear, you should know it because you may get questions for 1 mark. They may give an example and they may ask you what is its axial distance or axial angle or it's what type of crystal type. Okay, is it clear? Next we have to study is the packing in crystals. How the constituent particles are packed in a crystal. See, they should be packed in such a way that maximum space should be occupied. When they are closely packed, the energy will be less. Energy less means the stability of the crystal will be what? More. So before going into packing, I'm going to teach you what do you mean by voids. Okay. Now what is a void? Void is the space between the constituent touching particles. Now here, instead of using the word particles, I'm going to use the word spheres. Why? Because in the beginning itself we'll have told you, the particles, that is atoms, molecules or ions, we know they have got what shape? Spherical shape. So instead of using the word particles or just specifying atoms, molecules or ions, we'll be using the word what? Sphere. So what is a void? The space between the touching spheres is known as void. Spheres here is what? Nothing but the particles. And what are the particles? Atoms, molecules or ions. Now see here, I'm drawing. Now here how many spheres are touching? 3 spheres are touching. That means the 3 constituent particles. After the 3 spheres touching, some vacant space is coming. See the shape of the space. It has got what shape? It has got a shape of a triangle. So this we'll call it as triangular void. So understood what is a void? Void is the space between the touching spheres. Space left between the touching spheres. So the void here is what? A triangular void. So when three spheres are touching and the space coming is known as what? Triangular void. So understood what is a void? Void is the space left between the touching spheres is known as what? Void. Next here, see. Perfect diagrams I'm not able to make. Here how many spheres are touching? 4 spheres. The space formed by 4 touching spheres. It has got the shape of a tetrahedron. So this is known as tetrahedral void. The void formed by 4 touching spheres is known as what? Tetrahedral void. And the void formed by 3 touching spheres is known as what? Triangular void. Next you see here. Now the void, here how many spheres are touching? 6 spheres. So the void formed by 6 touching sphere has got the shape of an octahedron. So it is known as what? Octahedral void. So these are the 3 different types of voids which you should be familiar, which will come across when the constituent particles are packed. So void is what? The space between the touching spheres is known as void. The first one is known as triangular void, the void formed by 3 touching spheres, and the void formed by 4 touching spheres is known as tetrahedral void, and the void formed by 6 touching spheres is known as what? Octahedral void. So on this basis, next topic I will be discussing is packing in crystals. Packing in crystals. First, we'll study it in 1 dimension. Packing in 1 dimension. 1 dimension means how? Which axis? Only x-axis will be taking. Okay. So, packing in crystals in 1 dimension. That means we'll be taking only x-axis. See here. So here the sphere is packed in only 1 axis, that is the x-axis. So each sphere is touching the other. So this is in 1 dimension. Now here you have to be familiar with one more term, that is coordination number. Now what do you mean by coordination number? Now you just take the sphere itself. It is in contact with how many spheres? One on the left side and the other on the right side. Now again, if you take this sphere, it's also in contact with how many spheres? 2 spheres. If you take this sphere also, it's in contact with how many spheres? 2 spheres. Now if you take this sphere, this is also in contact with how many spheres? 2 spheres. So what is coordination number? The number of spheres which touches a particular sphere in a packing is known as what? Coordination number. So the coordination number for this sphere is what? 2. Now, if you take this sphere, its coordination number is also what? 2. At the end, there will be, it's infinity, isn't it? It goes like that only. So, the coordination number for a particular sphere in 1 dimension is how much? 2. Is it clear? So, coordination number is number of spheres which touches a particular sphere in close packing. Number of spheres which touches a particular sphere in a close packing is called coordination number. So coordination number is number of spheres which touches a particular sphere in a close packing is called coordination number. So coordination number in one dimension is how much? 2. That is, each sphere is in contact with 2 other spheres in close packing. So its coordination number is 2. So in case of one dimension, the coordination number is 2. So this much is clear. So next we'll go to close packing in 2 dimension. Now see here, packing of crystals in 2 dimension. 2 dimension, you see, this is in which axis? X axis, and this goes in which axis? Y axis. So it's in 2 dimension. So how I have arranged? I have arranged the first layer, and this I am going to give it as A. Now how I have arranged the second layer? The second layer is arranged just below the first layer. So it is identical to the first layer. So this also I am going to give it as what? A. Then the third layer again it is arranged just below the second layer. So that is also identical to what? The second layer. So that also I am going to give it as what? A. So one below the other I have arranged. Now I am just going to take a particular sphere here. I am going to take this sphere. Now this sphere is in contact with how many spheres you see? Here 1, 2, 3, 4. So how many spheres are touching? 4 spheres. So it gives you the shape of what? A square. So this is known as what? Square close packing. Now if you take this also, you see, the sphere is also in contact with how many spheres? 1, 2, 3, 4. So this also gives you the same shape. So this is known as what? Square close packing in 2 dimension. Square close packing in 2 dimension. Is it clear? That is, first layer you are arranging. The second layer is just arranged below the first layer. The third layer is arranged just below the second. So the fourth will be arranged just below the third. So it goes like that only. So each sphere you see is in contact with how many spheres? 4 spheres. Here also you see each sphere is in contact with 4 spheres. So what will be the coordination number? So the coordination number for square close packing in 2 dimension is how much? 4. That is, each sphere is in contact with 4 other spheres. And you see the type of void you are getting here. 4 spheres are touching. So the void is also what type? Tetrahedral. So is it clear? So in case of square close packing in 2 dimension, the coordination number is how much? 4. That is, each sphere is in contact with 4 other spheres. So in the next class, we will discuss about hexagonal close packing in 2 dimension.